Welcome. Here we have a table of integral. The table of integration or of integral is important to integrate. Without it, you cannot integrate easily. Here we elaborated for you 27 formula for integration. These formula are known as fundamental formulas. You would do better to memorize some of them or all of them. The main problem in evaluating an integral lies in expressing the integrand in a standard form. But we are going to use a set of problems to illustrate the idea of integration. Here we have a set of problems. With these problems, it will be clear that integration is not difficult. Integration as such is not at all difficult. The real difficult lies in applying the necessary algebraic operation and using trigonometric identities needed for converting the integrand to standard forms. When we say standard forms, we refer to the table of integrals. Now let's start with the problem number 1. Problem number 1. Here we have problem number 1. We're going to integrate it. To integrate this integral, we use the fundamental rule of integration from the table. Look, we immediately applied the first formula, which is known as power rule. The first formula in a table here. The first formula has been applied. Let's apply it immediately, and then we will get the answer. Here n is 3. N plus 1 equals 4. 3 plus 1 equals 4. 3 is n here. Here in the table you see here n is 3. See here n is 3. N here. N plus 1. N plus 1. N plus 1. N plus 1. Good. N plus 1 equal 4. The answer is this question number 1. Let's go to the question number 2. This is question number 2. Number 1 already done. Now let's integrate this question number 2. To integrate this integrand of the question number 2, we have first to convert this radical in a form which is integrable. It is impossible to express this radical as a power. Let's see how we are going to do so. I first expressed this radical as a power. We convert this radical like this, and then this term must go over the fraction bar. When it goes over the fraction bar, the sign change. We have the negative sign. As you see here, we have a form of integrand which is easy to integrate. We can easily integrate this form by applying the first rule of integration here in table. We are going to apply this rule by adding 1 to n. Good. Let's show you. We add 1 to n. When adding 1, we obtain the answer as required. After adding 1 to this one, you obtain a half. Applying the property of fraction, the final answer is this. The final answer is this. Question number 3. Question number 3. Jump. The question number 3. Question number 3. To solve this question, let's see on table of integrals. Table of integrals, we are going to use this 19 formula. The formula will help us to to solve the problem. Applying it, we find the answer. Just we applied this formula from table of integration. Question number 4 is like question number 1. We immediately apply the first formula of integration. Let's look. The first formula of integration. First, put 5 out of the sign of integration. 5 out of sign of integration. Applying the first rule, 1 plus 1, because here we have 1 plus 1, right? Then the factor 2 as required. Good. As required. This is answer for the question number 4. Let's jump on the question number 3. Question number 3. Number 3. Sorry, number 5. Number 5. Already done. Here only number 5. Good. Number 5. Question number 5. Here we have a question number 5. Question number 5. We put these factor, these constants out of the sign of integration, and we stay with these. We are going to perform some algebraic operation to convert these into the integrable form. Let's look. The second step is this. Now observe carefully. You see, this x square must go over the fraction bar by changing the sign from positive to negative sign. These are a necessary transformation, algebraic transformation. And now find good. See, now we changed the integrand to the integrable form. This form is reintegrable. We simply apply here the first formula of integration by adding 1 and dividing by this exponent here, and just the integration is done. Good. Then the last step is this one. Last step is this one. After making this addition, we find here, we find -1. Here also we find -1. Here we are going to apply this power rule. When we have -1, like this, just as you see, I part this here. This -1 has been applied here, and remember this coefficient, this constant, then it's already done. See, our integration is already done like this. You see, before this step 1, second step, third, and the last one. Good. Question number 6. Question number 6. This is already done. Now, question number 6. If you are observing very well, this integrand is presented as an exponential function. When we have exponential functioning integrand, we use this formula here. Now let's apply this formula and integrate these given questions. See here, this given question can be easily integrated like this. See, we directly applied the formula, just we pull out of sign of integration. This constant here also already done. This is a question number 6. Then now jump on the question number 7. Question number 7. Question number 7. Question number 7. Already done. We are now here. Question number 7. Let's integrate this question number 7. You see that the integrand is in a form of the radical. We are going to transform this radical such as to have the exponential form like this, like this. This index become the denominator, this exponent become the numerator. Good. By transforming this integrand to the form which is integrable, it will be easy to perform the integral. Good. But here integrand is transformed, is converted into exponential form. This exponential form is easily integrated, and we simply apply the power of this first formula of integration. Just stand back here to our form. Let's show you the last step. This is the last step. You add these fraction like this one. You see, simply perform like this, and denominator, add denominator, find this. You know, here we invert this denominator, because we know when we have this, see, this is equal 1 multiplied by 5 over 8. 5 over 8. Then I take this, put this one. See, the same here. Here. Good. The last or the final answer is this one. As you know, when you have a rational exponent, we also can express this expression with rational or fractional exponent like this. This denominator goes here, and this numerator will become the exponent of. You can also present your answer in this form and write, if you want, write like this if you want. This is also acceptable. is also allowed. I need it. Good. I see. Here also, if you want, as the last step, can convert this like this. Good. If you want, but I decided to stop by here. Let's jump on the question number 8. 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 Already done. Now we come here to this question number 8. Good. Question number 8. Question number 8 is very easy. Very easy. We only apply the property of integrals called the linearity. Linearity means that each function here, each integrand here is integrated separately. Look, this one, this is integrated separately, this one, and the last. I integrate, or we integrate each integrand separately. Now, this is called the linearity, property of integrals called linearity. Now, after integration, we find the last step. We applied one of these formula, the integral of sine, integral of cosine, and so forth. See here, integral of secant square. This one, when we integrate secant square, we obtain tan x. Good, already done. The question was very simple. You see, this is answer of the question number 8. Let's now jump quickly on the question number. Let me clean blackboard. Question number 9. We again apply the property of linearity of integration. This means we integrate each integrand separately, alone, like this. See here, each integral alone. See here, see here. That's long. Now we apply the linearity. Good. We apply the linearity. Linearity means we integrate each integrand separately, alone. Good. This is integrate. This one, and lastly this one. This is called linearity. It's a combination of a function. When you have a combination of function, we integrate each function alone. This is called linearity. Now, last step is this is the last step. This is the last step using the table. Here we have a new idea to show. A new idea is the apparition of these function ln, Neperian function. This ln. Let's have a look on our table of integration. When we have table of integration, well, we have such a kind of here. Good. See, when we have a function like that, yes, its integral, its antiderivative is ln. Good. Call this ln because the derivative of this function give when we differentiate like this, when we differentiate ln, we obtain that function. Good. Here we simply apply the formula from integral. Here these 4, we pull these 4 out, and then there's a direct application of the formula. Good. This is negative questions, and let's get to the question number 10. Good. Question number 10 now. Question number 10 is presented as a radical. As you know, when you have a radical, we convert it to an exponential form. We write it like this, and then here we apply the power rule or the first formula of the table of integration from the table of integration. Good. Now let's integrate. Yes. We write it as an exponential function with the fractional exponent and this form is easy to integrate. Let me show the subsequent. The following step is this one. Is the following step. The strange idea, the strange point here, you may wonder why this A here, why this A here, why this A here, because to find this phi, you see here, we apply we applied this formula, by adding one. Now after adding 1, we get like this, because 1 plus 1, we find is the common denominator, then have 2 equal 3 over 2. Good. But where did this A come from? Let me show you from the table of integration. Look at here, from the table. When you have the coefficient here, this coefficient must come here under the fraction bar. There is other way to show. This is a method we will learn later called substitution method. When we learn this method, I will show you how to find this A. By using that method, it is easy to find the origin of A under the fraction bar. But now at this level, you have to know that when you have an integer here, or every constant, or any constant, you can put it here under the fraction bar. You write it as a ratio. Good. Now this is the following step. Now let's see the other step here to see the last step. The last step here. This one is the last step. Why? We can also continue, because let me show you here. When you have a base with a fraction or a rational exponent, can write it like that. This numerator become the index. No, this denominator become index here, and this numerator become the exponent here. And as you know, x to the power 3 equal x square, like this, times x See? And putting these in radicand, we have x squared like this. See? Like this. So this is a perfect square. It goes out of the radical like this. Applying these here, we can also write this like this. See, A. I'm going to apply this formula. Good. A x plus b parenthesis and a x plus b. If you want, you can write this last step like this. Good. This is the last step. Question number 10. Now let's stop by here. The other question and the problem in next video. Next video you have to subscribe or to go to our channel to follow continuously the solution of all of the problems. Next we will see the integration using trigonometric identity. We have other method, the method called the substitution, as said, is mentioned above, and after the last method called integration by parts. Thank you very much. See you in the next video.